So let's talk about when you get a tank. So we have already found that the problem of a simple rectifying circuit is that even though it only allowed the positive cycle to come to pass, it would then there's a long downtime, meaning that you have 55% of the time there's no supply power into the circuit. So if you want to have, if we would like to have a stable DC output, there must be a stabilizing component in the circuit. So the way of creating a tank is simply adding what? What is a tank in a circuit? A what? Yes, correct, a capacitor. So how do I further stabilize the output? As we said, we don't want it to move when there's no supply coming in. So the basic idea is very simple. You change the resistive load into a capacitor. So you want to taking whatever is being fed into the system and store it into a capacitor. So I'm adding a capacitor rather than having a resistor load for my circuit. So this will still be the input AC signal, the same input AC signal. So we use a capacitor load to store. So you use C1 to store charge. Okay? We're still assuming the constant voltage model, so I'm giving you VDON. Okay? About 0.8 volt. Okay? So what happened is that if I want you to draw, first of all, in a time domain, you typically, for capacitors, typically need to set its initial status. For example, you want to know what is actually when you buy the tank, you assume that the tank is what? Empty, right? So you assume that QC, starting with time 0, it's 0. So the same thing, we're going to do the same exercise. Other than having a resistive load, we're having a capacitive load. But now we want to look at, if I'm giving you also the sine wave, the same sine wave, that's being given. This is 5 volt minus 5 volt. Okay? If this is the case, I want you to draw the output response, V out, as a function of time. As a function of time. So let's try that. So what happened is that your output voltage would depend on the amount of charge being stored on the capacitors. Initially, it's 0, so we assume that it started at 0. And then when it hits the delta V, it hits this. So the turning point is still 0.8 volt. We know that turning point is 0.8 volt. Therefore, it will rise when the diode turns on. So let's say at the beginning, when T is smaller than, let's say, T prom, your QC, the diode's off, D1 is off, no charging current. QC, we haven't started charging yet, so QC equals to 0, therefore your output equals to 0. Right? So it should start at 0. It started at 0. And then what happened is that once it hits this delta T, so the second part is when T is larger than delta T to a point where D1 turns on. So then the current, you're assuming that the diode can provide whatever amount of current because we're assuming constant voltage model, meaning that it can supply any current to sustain the difference. Therefore, the circuit will look something like this. this is the capacitor. And then we'll be applying V in. Let me redraw this. Okay? So it would then actually follow, input would then follow, output would then follow input, right? Because there's only voltage drop across here. Again, we go to output. This is input. Output will follow input by a voltage difference of 0.8. Again. So it's going to follow all the way here. So there's zone 1, 2. So once it reaches peak level at t equals to t, 1/2 t. So let me be precise here. So the second period is only when it exceeds, when diode turns on, and then it reaches peak level. So 1/2 t and higher than t prom. So t prom is the delta t that we just did in our previous exercise. So let's think about what happened when it reaches peak level. When it reaches peak level, your inputs start dropping. Your level actually being charged up to the, look at your tank at the house. When it charges up to its peak level, what happens? You ever seen the tank behind the toilet? There's a ball, which the floating ball would then, what? What happened when it reaches peak level? It would turn off, right? Because then it will remain at this level because I'm charging it up, so you should remain at this level. There's no. So once it reaches this level, it cannot go anywhere above. It reached, let's say, this is 4.2. So what happened next is that when, in region 3, what happened is that when t is larger than, passing the peak, your V-in start to drop. And my VL remains at the peak level, which is VP minus VD-on. Here VP is 5 volt. I just want to give a general number. So this is the peak level. So your VL is also at its peak level of 4.2 volt, if I'm using the number. So this would then fix at 4.2. But your V-in start dropping, so this would then make the voltage on the diode become VL, I should say V-in. Remember, the voltage across diode is V-in minus VL, right? So this would then give me a number less than VD-on. That is to say the diode is then off. When diode is off, your equivalent circuit will look something like this. Open. So this will be your equivalent circuit at phase 3, right? So this would then be charged up to a level, QC will be charged up to your peak level. At this moment, your tank is full with this amount of charge, right? So what happened is that if I'm drawing the plot, is that it breaks away from the system and it will remain stable because there's no current going in, no current going out. So it's a floating tank. It's not connected to anything, so it should remain flat all the way. Okay, so this is region 3. For this circuit, that's your corresponding output. Okay, so then we see that this is exactly what we actually wanted because it flattens. But did anyone see problem with this? Is this a real scenario? This is when you're not home. What I mean by this is that, or you're not flushing your toilet, meaning that you're not using the tank. So I'm not adding the usage part, because anytime you, let's say if this is an example of having a tank at your home, remember that the supply come in and then it fill up the tank. And then it remain flattened, meaning that no one's using the water. So the real case is that you're actually, whatever you want to stabilize, you actually want to use it, right? You want to use the water. So you want to assume a model where you're actually using the model, using the reserves as being safe. So in real case, in real operation, this does not happen. You don't, the reason of setting up a tank is that you want to use the water. So in real operation, your circuit will look more like this. The circuit will look more like this. You still built your tank, and we still have our diode for rectifying and still connected to the supply, the AC supply from the system. Okay? Aside from having only a capacitor, you need to assume that you're using the water. So how much does one use is typically modeled, or how much does a circuit use is typically modeled by something called R load. So this is referred to as the loading capacitor resistance. So the loading resistance is to simulate how much does the circuit actually need, because anytime you rectify and you actually send it out to the adapter or battery charger, it needs to take in certain amount of loading. You need to supply a person, for example, you need to supply a person usage of water. So this is just a model of circuit where it needs, how much does it need? Does it take in for further application, further usage in circuits? So CLO is the loading resistance to simulate what you're offering to the user. Okay? If this is the case, there's slight modification on our response, on the output response. So we're going to do it once again. Let me use the front page. So we're going to do the plot again. There's a refinement as to what happened when there's no supply. So at the beginning, the first cycle is the same. You charge up. So they're basically time. This is your 1/2 T. And then I'm going to do the cycle like this. Do a few cycles because there's slightly more complication. Let's just do 2. Okay, this is the case. Let's look at what happens. As I said, if it follows the previous, there's a T prom here, and then it goes up to our next point, which is the half cycle, the peak level. Once it reached the peak level, we still have our origin, let's say 1, 2. So only refinement we need to look at is actually cycle number, phase number, phase 3, I should say. So what happened in phase 3 is that instead of having a floating capacitance, no one's using whatever's inside the reservoir or the tank, there's a loading. So what happened is that Let me refine number 2. So number 2, during number 2, your circuit will look something like this. C R load C1. So doing this operation, I want to mention one of the key things is that there's a diode current, there's a capacitor current, and there's the resistant current. Okay? So during phase 2, when the diode is on, when the cycle, in the on cycle, let's see if we'll do this on cycle. During on cycle, what happens is that your diode current is supplying both the charging and the resistance. So when the water plant is actually providing current, the current coming in from the water plant is supplying the ones that you're doing when you're actually taking shower during this period, during the morning, for example. If the water only come in in the morning from, for example, 6 to 12, when you're taking shower, you're also using the water from the water plant instead of using the tank, and it also filling up the tank. Okay, so it supplies both the usage and the storage. Okay, so this is a very important point, is that during on cycle, it will supply both the circuit and also it does the charging. So this charging, this is the charging current, and this is the loading current. Okay? So what is the charging current? What is the charging current? So IC should equals to C1 dV out dt. Because your output is actually ramping. So it depends on how fast is the ramp. It has to, when it follows, it has to apply, make sure that your supply current is high enough, your diode current is high enough to supply that. In most cases, we're assuming that whatever is being supplied by the diode, using constant voltage model, meaning that whatever supply is infinite. It's determined by the external, not internal. But you need to know the amount. The amount would depend on the size of your tank and how fast does it need to ramp. Ramping speed, okay, of your signal. So as I said, the total amount of current will then be ID, during this period will be ID C1 dVL dt plus VL all that. And we're assuming that it will be sufficient, the diode current is large enough to supply this current. So if I ask you to calculate the amount of current, you should be able to write that, because that's the total amount of current that's coming in to supply both your shower and your charging, the filling of your tank. Okay? So in region 3, we don't need to talk about region 1, right? So this is D1's off at the beginning, so we don't talk about that a little bit. We're going to talk about number 3. So during number 3, phase 3, what happened is that your circuit will then, this will be off. And then this is how the circuit will look like. This will be open. You will be disconnected from the supply line, right? This is disconnected, and this is C1. So your tank is full at its peak level. The tank is full, and then you still need to use the water. So what happened? Where does the, yes, you discharge. So what happened is that this would then be coming, this will be IR, this will be IC. So IR will simply be minus IC, meaning that you're discharging we're discharging the capacitance C1. We're using whatever reserve we put into the tank, and then you start use that, right? So that's what it basically means. So what we actually want, so this is very critical because we want to know how low does it go? Does it affect does it affect the operation of circuit? Because circuit typically need a certain amount of voltage for it to work. For example, if the reserve is too low, you may not have enough water power to, clean up the wall or something. You need a sufficient an amount of water power to do something. Then if it drops too low, then it means that the fluctuation is too large, so that it will not sustain the function of circuits. So we know that it starts dropping. So during phase 3 is discharging. So this is when D1 is off. So when D1 is off, what happens is that you will then use the discharging current to support the R load. So let's look at what will happen. So I want to draw the line to find out what is the corresponding response. So there's only two current. One is IC. As I said again, because it's discharging, is VL C1 equals to minus IR, which is VL R load. Okay? So then we have an equation, looks something like this. You have a differential equation, solve for V out as a function of time. So this equation will look something like this. If I'm rewriting this equation, this will be V out as a function of time, dt equals to minus VL over R load. Okay? So what does that mean is it will stop dropping. So you solve the differential equation, you can solve for VL. I'm using a T prompt because I want to start at, I'm not using T prompt. Let me make sure that it's not confusing. So let me change this. So this will be delta T. We have already used that. So this will be your delta T point. Okay? Let's say I'm using delta T so that it will not confuse it. This would change to delta T. Delta T. Okay, sorry, because we're using delta T here. So if I'm defining something called delta T, anchor is at here. So I'm assuming that this is delta T prime equals to 0, meaning that T prime equals to T minus, starting from the center, starting from the peak level. And it's supposed to drop, right? So because the cycle starts at T prime equals to 0, meaning that at 1/2 of the cycle, so that, did I miss something? Okay, good. So then we can actually write this as VP, that's the peak level, VD on, exponential minus T prime R load C1. So what do you expect your output will be? It will be dropping from the peak point. This is boundary condition. When T equals to 0, it starts at VP minus VD on. That's your peak level. So this will tell us that at this particular point, your level is VP minus VD on, right? And it's supposed to decay exponentially. So starting from this point, it will decay exponentially. So it's supposed to go like this. Okay, so that will be your period 3 when the diode is off. So when it's dropped to a certain level, what happened is that, so this will follow that guideline, which will be VP minus VD on. Let me, if I'm using, okay, this is just right. Exponential minus T prom, those C1. Okay? So when it dropped, I didn't draw it exponentially because it typically takes a long time for it to drop to very low. Typically, you don't want it to drop it too low. So I'm going to talk about that a little bit. So what happened is that it will actually, when it reaches, when the second day comes, you then enter when the difference between the two. So at this particular time, let's say, let me label it as T1. So at this particular time, what happened is that when the difference between the two, when input starts to rise and your output drops, right? So when the difference reaches VD on, what happened is that the diode turns on again because the diode voltage is input minus output, right? Input minus output. So when input rises and your output drops, what happened is that it will then turn on again. So then it will then cycle again. So during this period, it will go back to charging. So this will be the same as number 2 when diode turns on. The only difference is that the first number 2 is that when you buy the tank, so you start charging from 0. But now you don't need to drop to 0 because there will be some water remain before the second charge up. So this is the second day after the tank is being filled and used and then filled. So you don't need to go the whole way, just the halfway when it's partially filled. And you didn't empty the tank. We don't want it to empty the tank. If you empty the tank, meaning that your tank is too small. Okay. If you use too much and at the end it drops to 0, then the tank is too small. So typically, we want to make the difference as small as possible, this difference as small as possible so that you don't actually feel the effect of having the drop on tank. Okay? So basically, let me, so there's basically return to, yeah, so this is return to D1 on. So this is when D1's on. So this is the off region. So we're really concerned. Doing on, you don't actually care too much because you actually have large amount of supply, and then it can sustain whatever your need is. Meaning that you can take your shower or anything. It does not dry out the tank. It does not empty the tank. But when you need to be concerned is the off time. So when it's off, then we need to be concerned whether there will be sufficient amount of charge for us to use, right? So one of the things in this type of application is that in this type of circuit, one of the key parameters is this. So we know that it's going to repeat itself. It's going to drop slowly, and then it's going to come up, dropping slowly. It will look something like this. So in this type of application, what you're concerned is actually this is the concern. This is how much voltage difference. I believe the textbook used this, defined as we call the ripple voltage. It's a little bit slight confusing with the reverse voltage, but they use in the textbook they use it uses this notation. Okay, so how does one determine how much ripple voltage there is? What are the constraints that will affect how much ripple you will experience? So let's first do the math, and then we'll come back and discuss it in a more intuitive way. So basically what we do is we go back to this equation. What is the ripple voltage? You could actually solve this, just simply use that exponential equation and the sine wave, but that will make our job too complicated. So in most cases, we still need to do analysis based on typical design, unless you make a very poor pick. Otherwise, these type of approximation actually pretty accurate. So in most designs, what you actually want is to make sure that the usage of water and the size of the tank is comparable to a level where there's not significant drop, meaning that you're not empty the tank too much. So that in a circuit sense is that you typically make your RC time constant. This is your RC time constant, meaning the amount of water is being stored and the usage of the tank, you could estimate the time should be much, in most cases, it's much larger than this period. Let me label this again. So I have T1, this point, and I have T3. T3, okay. That's fine. So between these two periods, I want to make sure that it's much larger than the period of discharging, T1 over T prime. I want to make sure that this is the time when it's off. This is the off time. You want to make sure that your tank is large enough to sustain your off time in most design. So that is to say that the equation, your VL, as a function of T prom, that T prom, I should say, let me not use T prom because T prom is a variable, so I'm going to use, if T1 minus the first 1/2, the peak time, the time when your tank peak, this is your off time. So it's larger than off time, therefore the equation will look something like this. Once again, I'm going to use a Taylor expansion and use the first order term. So it will be 1 minus x. This is minus x. So 1 minus x will be RC1 over T pro. Okay? So the next approximation is that what is the worst case condition is that there is a small difference between the charging period. So most of the time, we assume that we know VL at T3. We approximate it as VL at T1. We assume that they're actually close enough. This simply means that I'm approximating this point the same as this point. I'm using this point because it's easier to calculate. I don't want it to know precisely when it turned on. I'm assuming that it will take the whole period, the off time. I'm actually expanded. It's more like a worst case condition. Okay? So then the ripple voltage is defined as VL at T1 minus VL, I should say VL at the peak level. It's peak level and V out at T1. And I'm using this to substitute. So at T3, actually T prom, at T3 is actually a full cycle. So it's a full cycle. If you think about it, T3 in scale of T prom is a full cycle. So I'm simply insert that in. So this will be my peak level. Let me write down this. This is the peak level. I know I start at the peak. This is the peak level minus the drop. So it will be VP minus VD on 1 minus T there's a few approximation. Once again, I'm assuming that I'm supposing to insert T1 here, but instead I'm using the full cycle. I'm assuming that there's very small time between T1 and T3. So actually there's very small difference. So I'm just inserting this into here, right? I'm using the time extended to the full cycle to do approximation. So then I can actually get the final results. So your ripple voltage will be approximate. This is a linear approximation. So it's approximated by your peak level, the full tank level, times the ratio of R's. Because we get rid of this, there's a 1, so this has been canceled, and that's what's left. So we can check the numbers. This is in voltage, this is a ratio. This is the time, this is time. The RC is a time constant, T is your full cycle. Okay, so the other way of writing this is sometimes you see it in frequency, it will be inverse of frequency. So it will be also VP, that's your peak level. If you want to write it in terms of frequency. Okay? So what does this equation mean, or what does provide in a more intuitive sense as to what it does is that it tells you that if you want to make your ripple as small as possible, of course it's proportional to the peak level. So what's more interesting, rather than the absolute ripple voltage, what is typically more important or more meaningful is actually the ratio. So the ripple versus your peak voltage, if I'm rewriting it this is a percentage of fluctuation in your output. So this is the percentage of delta V, right, at your output. This is the thing that we're delivering out into the adapter. So you're typically more concerned about the delta, the percentage of variation. So what determines the percentage of variation based on this equation is so how does one choose their tank? So if you're a designer or you're the person deciding how large your tank should be, the consideration is how many people is at my house, meaning that it will depend on our load. Okay, so if there's more person, meaning that your loading resistance is smaller, meaning that it's taking on more current. And then it will depend on how frequent does the water plant provide water. Okay, so this is the same as if you're if you're engineer and you determine to build a reservoir. So depending on how long is the dry season, and then how many people is actually using this reservoir. So it's the same thing. So this will then determine, how does one determine this? Well, based on the spec. What is the spec? It's what is being required of you to deliver a stable output. Okay? I don't know if I have time to go through the example. But let's try. I wanted to go through an example. So as I said, this is very, very important. In a diode circuit, what you need to know is, once again, when it's on, where is it on cycle, where is it off cycle? When the diode's on, what happened? Does it provide charging current or diode current or discharging behavior? So let's see if I can run through an example. There's actually two ways of expressing a load. meaning that estimate how many people as are using the tank. One way is using a loading resistance, the other is using a loading current. So here I'm using a loading current because it's actually easier to analyze because your output will be a linear, except from having an exponential decay, it will actually be a linear equation. So this actually will give you a much easier output response. Okay. So let's still, this is your VDON at equals to 0.8 volt. So I'm giving you this as input as VP equals to 5 volt, V in. And then we have a cycle of 0.2 millisecond. I'm having C1 equals to 1 nano. It's not a very big tank because this is fairly, frequency is high. If you have low frequency, as the lower the frequency, meaning that the supply is not coming that often, you need large tanks. In this case, this is a fairly, in rectifying mode, this is actually high frequency signals. Therefore, I don't actually need too much. Okay? So if I give you an example, it looks something like this. The specific usage, this would define how many people are using this tank, the size of the tank, how frequent does the supply comes in. These are the definition. You should be able to find, first of all, want to find VR. And second, ID max. This is also important, is that how much does you expect the supply can supply the maximum current. And then this is sort of like a trick question. Average diode current. Over time, over the whole period, what is the total amount of, did I misspell it? I should say, if I'm assuming an average diode current, instead of having a fluctuation diode current, what does it look like? Okay? So how does one approach this problem? This is I actually give this out in a midterm exam, at least. I remember maybe a few years ago, and a lot of students reflected that this is very hard because you cannot use this you cannot use that equation because it's not the same thing. So how does one approach this type of question when there's actually more easy to analyze in linear, in time mode, rather than using the equation? So it's not suitable for equation. I don't think I have time to go through it, but I will encourage you to try. But I'm just going to give a hint as to how does one approach this type of question. First of all, what we want to know is that you still want to emphasize what happened in phase 2 when the diode's off. That will actually determine how much drop there is. So if you think about during phase 2 when D1 is off, when D1 is off, you draw the circuit. The circuit will look something like this. C1. And it was starting at this T prom point, V out at T prom equals to 0. The peak level will be VP, still the same, VP minus VD on. So in this case, it will be 4.2 volt. So you know that it started at 4.2 volt. So if I'm drawing T prom, I'm only drawing the off cycle. It will then start at T prom equals to 0. We know that it starts at 4.2 volt. Okay, I'm rescaling at T prom equals to 0. And then it's supposed to drop, right? That's assuming that at a full cycle, what is the dropping rate? If I'm drawing this, the current, remember IC plus IR equals to, I low equals to 0. So IC is C dVO dt equals to I load. So what does that mean? It means that in this case, it's a linear response because my slope is fixed because I load is the same. So I could actually just insert a number. This will be 1 micro. This will be 1 micro amp, and this is 1 nanofarad. So it's actually dropping. Did I have that? Dropping in a rate. Because there's a minus sign here, so this is a minus sign. So it's dropping at a rate of minus 1 volt per millisecond. Okay? So you know the slope. Through this, we can get the slope, which is 1 millivolt, minus 1 millivolt per millisecond. Right? So what's our cycle? Our cycle is 0.2. So this is 0.2 millisecond. So it's only dropping by how much? You just time it up. So for a full cycle, it will drop. I already know the slope. I already know the period. So this is simply 0.2 volt, minus 0.2 volt. Did I get right? So meaning that it will drop from 4 to 2, 4.2 to 4. Your ripple voltage is about 0.2 volt. Right? Actually, I think we can actually go through that. 5 minutes. I think we can do this in 5 minutes. So the second part is then, so you get the slope and then you can get the projection and find out the ripple voltage. And this is of course approximated assuming that there's very little difference because it's very close to the peak. So you can still use the same approximation as we did that for a resistive load case. And then for the part B, what is ID maximum? ID maximum is when the supply is coming to supply both this and that, both RC. So that will happen at when? When do you think it will happen? Let's write down the equation. Plus IR. Do you think it will happen at the beginning or at the end? This is a little tricky because your output voltage, your supply voltage depends on at the end. But this will depend on at the beginning of the charging period. But anyway, in the chart, let me say this. This is in this phase. We'll not consider the first charging period, we'll only consider this one. So you're assuming that I1 in region 2, this is in region 2 with diodes turned on. So you're assuming that it's actually happened at this particular point. Because at this particular point, you actually have the fastest ramp rate that will lead to high current. I don't think I have time to go into that. Let's come back to that next week. But just to give you a sense as to, there will be some small difference in, oh, sorry, this is the loading current. So my loading current will look the same, but the difference will be when does the charging actually happen the fastest. So if I ask you to draw something like this, let me draw the plot. Let's say this is my signal. Let me just give you a qualitative description. So what happened is that my cycle will look something like this, right? As we already labeled, it will go something like this. It will drop only a little bit. Okay? So during this period, this is the on period, this is the off period. So there's only two periods because we're not considering the initial part. So there's only on, off. During the on period, during this period, it's supposed to be 1, if I'm following that. If I'm drawing current, ID, as a function of time, it will look something like this because it depends on the ramp. So at this, when it's flattened out, when you're reaching the peak level, meaning that you actually, there's no need of charging current. So at the peak of sine, its derivative is 0. So you actually see something like this. When it's off, of course, it's 0. And then it will only start charging. So this will be 0. It will only start charging. It will jump up when it turns on. And then it will drop to low. And then drop. I don't know if this is clear enough. I will explain a little bit. You always have a baseline because you need to supply a base of I load. So there's a flat I load plus a, I should say cosine, because the derivative of sine becomes cosine. So part of the cosine plus a I load. So that's how you get that. So we'll need to find the peak level when we find out this time. You need to know the time in order to get the peak. So it's slightly more complicated. But I'm just giving you a sense as to what needs to be supplied. So on the onset of turning on the dial, it will actually give you the peak dial current, and it will drop because it's a cosine. Cosine will drop at this peak level. And back to only I load. Okay? So let me end it here, and then we'll come back on Tuesday on the just to really finish up chapter 3.